Hello everyone. In this video I'm going to be talking about separable first order differential equations and just going over a few examples of solving some. So let's get into it. So my first example, and I have three examples in this video. The instructions are this. Just simply solve the given differential equation by separation of variables. So a first order differential equation, I'm going to write this off to the side first, is separable. Right? It's called separable if it can take this following form. Right, so it might not start off looking like this, but you can manipulate the equation to look like this. We have derivative of y with respect to x equals, and then some function that depends solely on the independent variable x multiplied by some other function that depends solely on y. So like the variables are separated, and if this is the case, then you can manipulate the equation so that you get all terms with one variable on one side with its differential, and all terms with the other variable on the other side. Thus the name separation of variables. And you want to make sure that the differentials are in the numerator. So I keep dy over here. I would keep dy over here and then divide by the function of y, get dy divided by g of y, and then multiply by the dx, the differential of x, and get f of x times the differential of x, and then you would integrate in order to be able to solve the equation. Now this manipulation I just did, multiplying by dx, treating dy over dx as a fraction and whatnot, those manipulations with the differentials dy and dx, you can only do those with first order differentials. Alright, so if this were the second derivative, I couldn't do that. If it were the third derivative or any higher derivative, I couldn't do a manipulation like this. You can't treat it like a fraction. Again, you probably saw this in Calculus 1 or Calculus 2. You can only do this kind of manipulation with first order differentials. Alright, so just to show you that this particular equation here is separable, I'm going to play with it and get it to look like this. Right. So we have dx plus e to the 3x times dy equals 0. So I'll just take away the dx. We have e to the 3x times dy would be equal to the opposite of the differential of x. Then dividing by dx, dividing by e to the 3x, we'd have dy dx equals negative 1 over e to the 3x, or negative e to the negative 3x, if you want to look at it that way. And I guess one other thing to point out too is that the variables don't have to be y and x. All right, just know that. Sometimes it might be y and t, or s and r, whatever. Just know that the variables don't have to be y and x. You may come across problems with other variables, but that you still treat it the same. So you see I've got my first derivative of y with respect to x on the left, like this, and then you have over here on the other side, see there's a function of just x. This would be f of x here, this negative e to the negative 3x. And then the function of y, I guess you could say, is just the number 1, if you wanted to. Right? Because you can put a times 1 on anything and it won't change the value, and we'll call that's g of y. So you see I do have a separable equation, because I could make it take this form. Alright, now I'm asked to solve this thing. Alright, so here's where the separation of variables comes in. So I leave dy on the left, and divide by 1, I guess, right? But there's nothing to do there. And then I move the dx to the right with this function of x. So we have negative e to the negative 3x times dx. And now the variables are separated, right, with their respective differentials. And then we integrate. So these are indefinite integrals. So I take the indefinite integral over here of 1 with respect to y. And over here the indefinite integral of negative e to the negative 3x with respect to x. All right, and I'm hoping that you remember a lot of your integration techniques from Calculus 1 and Calculus 2, because you're going to be having to use probably all of them at some point when practicing problems in separable equations. So you got your u substitutions, integration by parts, trig substitutions, integration by partial fraction. When you have rational functions, you have partial fraction decomposition, and all sorts of things. All right. So here, these are pretty simple. So I'm just going to write out what they are. On the left side, the integral of 1 with respect to y would just be y. Now technically it would be y plus some constant of integration, right? Plus c, but you're going to be doing the same to both sides. So I'll have some constant added to the left and some constant added to the right. And you could just subtract this constant and make a new constant over here. So rather than have the plus c on both sides, I'm just going to do it on the right side, on one side. Okay. So y on the left, and then pull the negative out, you'd have e to the negative 3x, and then times negative 1/3, but then times this negative 1 to make it positive 1/3. So there's the antiderivative of negative e to the negative 3x. And you can double check by taking the derivative, right? It would be negative e to the negative 3x. And then again, plus some constant. Right, constant of integration. C is a constant. And, this is already solved for y. I've done it. I have found a solution, a family of solutions, a one-parameter family of solutions to this this differential equation. And if it weren't solved for y, if you end up doing something where the y is not alone, instead of it being an explicit solution, it would be considered an implicit solution. And then you could solve for y if you wanted to try to find explicit solutions, but this is fine. Right. So here's an explicit solution, right? Because again, y is solved for. The dependent variable is alone. Explicit, family of solutions to this differential equation. So this satisfies this equation for any value of c, right? Any real number value of c. Now, if you want to test that, right, let's check it. Well, I could take this here and say, hey, what's the the differential of y? Basically, take the total differential of both sides. The differential of y equals, this would be negative e to the negative 3x times dx, right, and then plus 0. And I guess I could substitute this into, in for dy in the initial equation and see if it's satisfied. Right, so we'd have dx plus, e to the 3x times this, right, the dy, and see if that's equal to 0. Well, indeed it is, right? You have dx, oops, I put a minus there, right? Forgot the minus. We have dx, and then e to the 3x times e to the negative 3x would be e to the 0, which is 1, but then you get the minus here, so we have dx minus dx equals 0, 0 equals 0. Check. All right, that's true. So this one parameter, family of solutions here, they are solutions of this differential equation. They do satisfy it. Okay. Great. All right, so that one was a pretty simple example, I feel, because the integration wasn't terrible, wasn't difficult to do. Again, I've said it already. Just know that some problems, may be a little trickier because you might have to, employ other techniques of integration that you've learned in Calc 1 and Calc 2. Alright, so here's another one. So we have y times the natural log of x times, this is the derivative of x with respect to y. Now we could also, again, manipulate this and get it in terms of, the derivative of y with respect to x. So I'm going to do that in a second, just to, again, show you that it's separable. Equals, y plus 1 divided by x, that quantity squared. Alright, so if I mess with this a bit, we have dx over dy equals, and then here, if I square the numerator, you have the quantity y plus 1 squared, and then I'd be dividing by y, so we have over y times, and then, we'd have x, a factor of x squared in the denominator, and I'd be dividing by the natural log of x, and then, 1 in the numerator. And if we want this instead to be dy dx, just flip both sides. Again, you can only do that with first derivative. All these manipulations can only be done with first order differentials. So if I want, if you're like, oh, I don't like dx over dy, I like dy over dx, I'm more used to that. You can just, take the reciprocal of both sides. dy over dx then would be y over y plus 1 squared, and then times, x squared natural log of x. And then now hopefully you can see that it is definitely a separable equation. I have my first derivative of, y with respect to x over here, and then on the other side you have some function that solely depends on x multiplied by some function that solely depends on y. Separable takes this form. Alright, and since it takes that form, it is separable, and I can separate the variables. So I'll leave the dy on the left, and then divide by g of y, or basically multiply by the reciprocal of this fraction here, and we get, the quantity y plus 1 squared divided by y, and then you have times dy. Equals, and then, move the dx to the other side, we have x squared times the natural log of x dx. Great. Alright, so the variables have been separated, and now I'm going to do, indefinite integration. So indefinite integral of y plus 1 squared divided by y dy. Alright, so I'm just going to do the left side first. Alright, I'm going to do the integral on the left first, and then we'll get to the integral of x squared times the natural log of x dx after that. Alright, so this one here, I see if I just expand the numerator, that'd be y squared plus 2y plus 1, then divide all that by y dy, and again just divide every term in the numerator by y. We have the integral of y plus 2, and then plus 1 over y. And now the integral hopefully becomes very simple. So on the left side, I'm going to have, half y squared, right, the integral of y, plus 2y, and then the antiderivative, remember, of 1 over y was the natural log of the absolute value of y. Now if you make a mistake here and just write the natural log of y, I wouldn't mark you off myself, but it should technically be, the natural log of the absolute value of y. Alright, so this will be the left side. Now again, there's a plus constant here, but like I said, I'm just going to put the constant on the right side. Alright, so this is going to be the left side. Alright, now let's look at the right side integral. I'd be integrating x squared times the natural log of x with respect to x. Alright, now this one here, we have a product of a polynomial, right, x squared, times a logarithmic function. Right. So, usually, right, when you have a product of two, usually, not always, but when you have a product of two different kinds of elementary function like this, it's usually a good idea to try to integrate by parts. So remember the little formula for this. In most textbooks, they're using the letters u and v. Remember, the integral of u times the differential of v was, u times v minus the integral of v times the differential of u. Right, and this kind of came from the reversing the product rule for derivatives. Right? All right, so now you have to make a choice of u and a choice of dv, and remember the differential dv will always include the differential of the integral, dx here. So here I'm going to have, now, remember you kind of got to play around with this sometimes, but your choice of u, you might have to mess around with. But if you remember, there was an acronym, LIATE, LIPTE, however you want to remember that. Like logarithms, inverse functions, inverse trigs, arithmetic or polynomial functions, and then trigonometric and exponential functions in that order. It usually works out if so like logarithmic functions over polynomial functions. So I'll have my choice of u be the log here. Again, I'm not going to get into all integration by parts too much. You should know how to do this. And then dv will be the rest of it, right? The rest of the integrand, x squared dx. And then du, right, would be 1 over x dx. And then v, integrating this, would be 1/3 x cubed. All right. So now applying the parts rule, this integral here will be the integral of uv, so 1/3 x cubed times the natural log of x minus, and then the integral of v du. So the 1/3 will come out of that, and then x cubed times 1 over x is just x squared. And that's a very easy integral to take. So we have 1/3 x cubed times the natural log of x, and then minus 1/9 x cubed. Right? Because it'd be 1/3 times 1/3 x cubed. And then this is, on the right side, I'll put the constant, right, plus some constant, c. All right, so here's the right side. And there we have it. All right, I'm going to write all this up on the next page where we're totally done. And this is definitely a family of implicit solutions. So we have on the left side, remember it was 1/2 y squared plus 2y plus the natural log of the absolute value of y equals, and then the right side, this crazy thing here, 1/3 x cubed times the natural log of x minus 1/9 times the x cubed plus some constant. Right, there's no way I'm going to be solving for y here. All right, there's a mixture of polynomial and logarithmic. So I'm not going to try solving for y here. This is it. All right. Once all the differentials are gone, the dx and the dy, you have a solution to the differential equation if you did everything correctly. And this would definitely be considered a family of implicit solutions. Right? Now, if you really want to check on this, you could take the differential of the left, the differential of the right, and see if it satisfies that original equation. Or we can also, all right, let's take a look at this. Going back here, remember this is how I had the dy dx. What I'm going to do now is I'm going to pull up a slope field generator. Remember slope fields from a previous video, direction fields. I'm going to pull up a slope field generator and enter this equation in here and see what the slope field looks like. Alright, and then I'm going to graph this implicit equation. I'm just going to let c be 0. You can let c be anything, any number. I'm just going to have c be 0, and we'll graph this implicit solution and see if it actually kind of like fits into the slope field for this equation. Alright, let me show you what I mean. Alright, so this is actually a different slope field generator than the previous videos. I used GeoGebra before. This is a slope field generator that was created in Desmos, at a place called desmos.com. All I did was Google slope field generator, and this was actually the first thing that popped up. Alright, so they're saying let g be the derivative, so they have the derivative here, and what I'm going to do is I'm going to enter our equation here. We have dy dx was equal to, I had y times x squared times the natural log of x in the numerator, and then divided by y plus 1 squared in the denominator. Alright, is that too much? Oh, I used backslash. I didn't actually divide. Alright, so let me get rid of this and type in y plus 1 squared in the denominator here. Alright, so this was our, oh come on. There we go. Now let's see, why is this so messy? Alright, I gotta delete this superscript. There we go. There. Alright, so here's a slope field. Sorry how long that took. And notice, it's only for the positive values of x. Remember, natural log of x, you can only plug in positive values of x. So you see how you only get slope, little lineal elements for the slope field on the right half of the plane. Alright, and it looks like they're only going, whoever created this only did it up to 10. I didn't create this. Right. I just found it. Alright, so now what I'm going to do is put into this next line here our implicit solution. Right, I'm going to put in this here with c being 0, and see if it kind of follows along with the slope field. All right, let's pull that back up. All right, so we had y squared divided by 2, right? Half y squared plus 2y plus the natural log of the I'll just put y, okay. So it only is only going to give me stuff with the positive values of y. I guess I could do absolute value of y too. Abs y equals x cubed divided by 3 times the natural log of x minus 1/9 x cubed. Alright, and look at this. And then plus some constant. Right. So if you look, see how this curve, the graph of this implicit solution, look how it follows along with these lines in the slope field. Right. Looks pretty good. Right. And again, whoever made this didn't make it past 10, but you can hopefully see how it's following along the direction of these lineal elements in the slope field. And down here as well. Right. Okay. And if you wanted to, right, oh, I just erased it. But yeah, you could have thrown on plus any value of c and would have seen a different curve that also followed the slope field pretty well. All right, so going back to my paper, yeah, and that's where I'm leaving that. Okay. All right, so I've got one more example for you. Sorry that this is running a little long, but just want to show you as many examples as I could. Obviously, I'm not going to get through every possible example you're going to come across, right? You're going to have to do more and more problems on your own. But I just wanted to throw out one with some trigonometry in there, some trig functions. All right, so this last one, we have a cosecant of y times the differential of x plus secant squared of x times the differential of y equals 0. All right, so same deal. I'm going to show you that it's separable. All right, so we'd have a secant squared x dy would be equal to the opposite of the cosecant of y dx. All right, if I just subtract that and then put the dx under the dy, so dy dx equals, and then you can divide by secant squared. You get negative cosecant y times 1 over secant squared x, right? Just to show that they're separate. There's a function of y times a function of x. But there's a much simpler way of writing that. Right? This would be negative cosecant y times, and then 1 over secant squared is cosine squared. Right? But either way, you're seeing that it's separable, I'm hoping, right? You have the dy dx equals some function of x times some function of y that are separate. All right, so I see that it's separable. It takes that form. And let me separate the variables now. I get the y stuff on the left and x stuff on the right again. So I'll keep the dy here. And then instead of dividing by cosecant, I'm going to multiply by sine. Right, because remember cosecant is 1 over sine. So I have sine of y dy. In fact, I'll put the negative over there as well, right, times the negative. Equals, and then the cosine squared x with the dx, right, moving the dx to the right side. Okay. And then we're anti-differentiating, right, indefinite integral. So I'll do the left side first. I'll just put ls for left side. All right, left side. So I have negative integral of sine of y dy. This would just be the cosine of y, because remember the derivative of cosine of y would be the negative sine of y with respect to y. And that's it. And again, you can put plus constant, but I'm going to just save it to put the plus constant on one side. So the left side is just going to be the cosine of y. Now the right side is going to be a little more involved. The integral of cosine squared of x with respect to x. So hopefully you remember. There's a lot of stuff I'm saying you got to remember. I know. A lot of remember all of your integration techniques and also trig identities. Because if you want to integrate cosine squared, it'd be easier to use a power reducing formula, involving a double angle. Remember, cosine squared is half of 1 plus the cosine of 2x. Right. The cosine squared of x, remember, was 1 plus the cosine of 2x divided by 2. And then I pulled the half out. And this is a lot easier to integrate. Right? This would be half of, and then the antiderivative of 1 with respect to x would be x. And then the antiderivative of cosine 2x would be half of the sine of 2x. Right? Using the thinking about the chain rule for derivatives here. Right? And then plus some constant when I'm all done. And if I want to, I'll put the half in. I'll distribute this half in a second when I write down the final solution. Okay. Great. So an implicit solution to this differential equation then is the following. We have the cosine of y on the left equals, half x plus a quarter of the sine of 2x, and then plus, plus any constant. All right. So here's an implicit family of solutions, one parameter family. An implicit solution to this differential equation. Right. Now you could solve for y here, wouldn't be too terrible. Just take the inverse cosine of both sides. The only issue being that whatever values of x get chosen, all right, this side over here has to be between -1 and 1 to take the inverse cosine. All right. So, I mean, either way, this side's going to have to be a value between -1 and 1, because remember, the cosine of anything is something between -1 and 1. So this side over here has to be between -1 and 1. So you could write an explicit solution to this. Y equals the arc cosine or inverse cosine of all this, of half x plus a quarter of the sine of 2x plus some constant inside there. And here's an explicit solution. And again, let me show you with now you could check it by taking the differential of both sides here, taking the total differential of both sides and seeing that it would manipulate it till you get it to look like this again. And you could, if you took the differential of this side, differential of that side, you could manipulate it and make it look like this again, I promise you. So this is going to satisfy that equation. But again, what I want to do is show you some slope field stuff. All right, so what I'm going to go back to that slope field generator, and I'm going to enter this. Right, when I got the dy dx equals negative cosecant y times cosine squared x. And then I'll graph the implicit solution. Well, I'll just use c equals 0 again. All right, and see if the solution follows the slope field pretty well. At least it should. Right. So back here for the y prime, right, for the slopes, I'm gonna put in we got negative cosecant y times cosine squared of x. And what's going on now? Oh, nope, it happened. Okay, so look at this crazy slope field, again, just on the window from -10 to 10 for x and -10 to 10 for y. Alright, so here's a slope field, and then what I'm going to enter now is our implicit solution. Right, we have the cosine of y was equal to half x plus a quarter of the sine of 2x, and then plus some constant. All right, but again, I'm just going to use a constant of 0. And if you look at this weird curve, see how it kind of follows the direction. You see this purple here, purple direction line. The curve's going that way, and then it's turning here, and then it looks like if you imagine the direction field is like the flow of water. The direction, this curve is following that direction field. All right. All right. And then when we look at, if I pull, now this is the implicit solution. All right, remember, there's a restriction if I take the inverse cosine of both sides, because the inverse cosine of some number is just going to be between 0 and pi. if you recall from trigonometry. So if I did that, right, if I go through this and take the inverse cosine of both sides, it's just going to be a little piece of it, right? Just the piece of that curve where y is between 0 and pi, right? So this is actually a piece of that larger curve we just saw, but only a little part of it. And there's an explicit solution to our differential equation. Okay. All right. So again, lots of stuff. You got to remember techniques of integration, maybe some trig identities, right? Lots of things to remember, but all these are set up the same though, right? I showed you that they were separable by putting it in that particular form. Then I separated the variables and did integration to find either an implicit solution, and if you can solve for y, you can find an explicit solution to the equation as well. All right. So hopefully looking at these problems help you when you're working on problems similar to this, and thanks for watching.